Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss in detail the way how to perform armature winding in a DC generator. So, before starting the actual armature winding process, I will discuss some very important terminologies, and these terms will be used in the armature winding process. So first term is called pole pitch, and pole pitch is the number of armature conductors per pole, right? So mathematically, pole pitch or YP is equal to number of slots divided by number of poles. If the stator of the machine has four poles and if the total number of slots in the armature are 32, then the pole pitch will be equal to 32 by 4, which is equal to 8. Next term is called coil pitch, and coil pitch can be defined as the distance in terms of armature conductors between two sides of a coil. And it has two parts, back pitch and the front pitch, right? So you can understand these two types of coil pitches in these figures. This is the back pitch, or back pitch is the distance between the two ends of a coil from the back side, right? This is the back side and this is the front side. Front side is also called as commutator side, and these are the commutator segments. So the number of slots which are spanned by the coil from the back side is called back pitch, and the number of slots which are spanned by the coil from the front side is called front pitch. So this coil ends over here and it starts, for example, from here. Then the number of slots between these two um, points or these two ends of the coil is called the front pitch. So suppose this is the slot number 10, this is the slot number 7, so the front pitch will be equal to 3. Similarly, if this is the slot number 5 and this is the slot number 10, then the back pitch will be equal to 5. So this is one type of winding, and this type of winding is called as lap winding. This is another type of armature winding, and this type of winding is called wave winding, right? So lap winding and wave winding are the two types of armature windings, and the difference between these two windings is that in lap winding, the front pitch is negative, right? So you can see we are moving forward and then we move backward, right? So the front pitch is -3 in this case. So that's why we have to come from slot number 10 to slot number 7 and so on. But in wave winding, both front pitch and back pitch are positive. So first we will connect this conductor with the conductor in this slot, and the separation between these two slots will be equal to YB, and then again we will move forward. So front pitch is also positive, and suppose this is slot number 10 and this is slot number 13, then the front pitch will be equal to +3. So that is the front pitch. So both back pitch and front pitch are positive in wave winding, and this is called commutator pitch. Um, so this is called a lap winding, and the reason is that you can see the two sides or the two successive coils are overlapping with each other. This is the first coil, suppose, and this is the second coil, and we can see the overlap between the two coils. So that's why this winding is called lap winding, and here we don't see any lap winding. So these windings are ever moving forward, so they are called wave winding. Now another term is the resultant pitch. It is the distance between the beginning of the next coil and the beginning of the previous coil to which it is connected. So suppose we are doing the winding from right to left. Now this is the beginning of the first coil and this coil ends over here, and this is the beginning of the next coil. So the resultant pitch will be the number of slots between the beginnings of these two coils. So that is the resultant pitch. Similarly, in this case, the resultant pitch will be that much. So the beginning of first coil is from here and the beginning of the next coil is from here. So this is the resultant pitch. And last is the commutator pitch, and it is the distance measured in terms of commutator segments between the segments to which the two ends of a coil are connected. For lap winding, commutator pitch is equal to back pitch minus front pitch, and for wave winding, commutator pitch is equal to back pitch plus front pitch. So as I have said, for lap winding, the front pitch is negative, and for wave winding, front pitch is positive. And here you can see this is the commutator pitch, and here the commutator pitch is bigger as compared to the commutator pitch in this case. So these were some important terminologies, and now I will move towards the lecture on armature winding. So I will discuss both lap winding and wave winding in this lecture. So first of all, there are two types of windings as far as the number of layers are concerned. So first is called single layer winding, second is called multi-layer winding. If we have one conductor per slot, then this is called single layer winding. If we have multiple conductors per slot, then this is called multi-layer winding. And we have to draw the developed diagram in order to understand the armature winding, right? Developed diagram is that kind of a diagram in which the whole circular or cylindrical periphery of the armature is shown on the page, right? So actually the armature is cylindrical, but we can show the whole armature core and armature slots and the poles on a page, right? Or on a plane. So that diagram is called as developed diagram. And we have discussed a simplex lap winding in which four poles are considered. Number of conductors are equal to 16 and the number of slots are also equal to 16. So it means we are performing single layer winding. Back pitch is equal to pole pitch plus 1 and front pitch is always assumed as pole pitch minus 1. So in our case, pole pitch is equal to 4 because 16 by 4 is equal to 4. So the back pitch will be equal to 5 and front pitch will be equal to 3. So let's start our winding. And first of all, we have to draw the poles. This is the North Pole, this is the South Pole, and this is the North Pole, and this is the South Pole. So these are the four poles. But we have to draw this first pole again over here because the stator of the motor is cylindrical. But we can draw this first pole again, and in this way we can draw a clear figure or a clean figure of the armature winding which will be clearly understandable. So since we have the pole pitch equal to 4, it means there are four conductors which are in front of one pole at one time, right? So first four conductors are in front of this north pole, second four conductors are in front of this south pole, then the next four conductors will be in front of this north pole, and the next four conductors will be in front of this second south pole. And again, we will draw these first four conductors in front of the first north pole. Now we are given back pitch equal to 5. So let's start our winding from slot number 1. And our first conductor will be in the first slot, and from the back side it will span 5 conductors, right? So after 5 slots, we will be doing the connection of this conductor with the slot number 6, right? Because back pitch is equal to 5, so 1 plus 5 is equal to 6. So this conductor will be connected to this conductor from the back side. Similarly, front pitch is equal to 3, so the conductor in slot number 6 will be connected with the conductor in slot number 3 from the front side or the commutator side. So this is our first coil which is completed. Now the second coil will start from here, and 3 plus 5 is equal to 8. It will be connected with the conductor in this slot, and 8 minus 3 is equal to 5. So that will be connected with the conductor in slot number 5. Then it will be connected with slot number 10. Then we will come to slot number 7. Then slot number 12. Then slot number 9. Then slot number 14. Then slot number 11. Then slot number 16 and slot number 13. Then slot number 2, because 13 plus 5 is equal to 18. So since the total number of slots are equal to 16, so 18 number slot will be the second slot because this is a circular periphery of the armature. So we will connect this conductor of slot number 13 with the conductor in slot number 2. Now that will come 3 slots before, and it will be connected with the conductor in slot number 15. Then we will connect it with slot number 4, then slot number 1. So we started our winding from slot number 1 and we finished our winding at slot number 1. And in this figure, you can see that no slot has been missed. Here you can see the slots number 1, 2, and 4 are empty from the front side, but they are connected over here 1, 2, and 4. Similarly, slots number 2 and 4 look empty over here, but they are connected over here. So this is a complete diagram and no slot has been missed and there is no repetition of slots. So all the slots have been considered only once. So this is a single layer winding. Now we will draw the commutator and we will place the insulation between commutator segments. Each coil end will be connected to one commutator segment, unique commutator segment, and between commutator segments there will be insulations and we have to mark the direction of the current. So in front of North Pole, we have assumed the direction of current to be downward, and in front of the South Pole, we have assumed the direction of current to be upward. So that direction of current actually is determined by the direction of the motion of the conductor or the direction of the rotation of the armature, right? So that direction of the rotation of the armature together with the direction of the magnetic flux will determine the direction of the flow of current. But we can assume that the direction of current over here is downward. It means the direction of current in the conductors in front of the south poles will be upward. Similarly, this is downward, this is upward, and this is downward. And now over here, we can see the current is coming down, and over here, current is going upward. Here you can see the current is going upward, and here again the current is going upward. So uh, that current or that segment of the commutator is actually receiving the current from the external circuit. So we will place a carbon brush over here. At this segment, we don't need any carbon brush because there is no net current coming out or entering this segment. So the current which is coming to this segment is actually equal to the current which is leaving this segment. So this is called a dummy segment and there is no need to connect any carbon brush with this commutator segment. Here again, current is going downward and current is going upward. Here you can see current is coming down and here current is also coming down. So that commutator segment will provide the current to the external circuit. So we will need a carbon brush over here. And here again, there is no net current to this commutator segment. So no carbon brush. Here again, the current is going upward uh, in both the conductors connected to this commutator segment. So we will need a carbon brush over here. This is also a dummy segment and this will be the commutator segment which will provide current to the external circuit. So this carbon brush and this carbon brush, they can be joined together and this carbon brush and this carbon brush, they can also be joined together because they are providing the current and these two segments are receiving the current and this will become our positive terminal of the DC generator and this will become the negative terminal of the DC generator. So this is how we can perform lap winding uh, in the armature core of a DC generator. And now we will have to examine the number of parallel paths, right? So number of parallel paths can be evaluated by going from the negative terminal to the positive terminal of the DC generator, right? So this is the negative terminal. And from here you can start counting the number of slots, right? So let's see, we have started from this conductor, right? So first we will move to conductor number 5, then we will move to conductor number 10, then we will move to conductor number 7, and then we will move to conductor number 12, and then we have reached the positive terminal, right? So 5, 10, 7, 12, and 5, 10, 7, 12. This is our first parallel path. Now we can start counting the conductors in this direction, okay? So in this direction, the first conductor is the conductor number 8 and the second conductor is the conductor number 3. The third conductor is the conductor number 6 and the last conductor is the conductor number 1 and from here we can see that after the conductor number 1 we have reached the positive terminal, right? So this is our another parallel path and we can do the same for this commutator segment because this is also our negative terminal and this will constitute the third parallel path and this will constitute the fourth parallel path. And in total, we will have total number of parallel paths equal to 4, right? So a number of parallel paths are represented by the capital A, and for lap winding, the number of parallel paths are equal to the number of poles, because in this figure you can see number of parallel path is equal to 4, and the number of poles are also equal to 4, and the number of carbon brushes are also equal to 4. So in lap winding, number of parallel path is equal to the number of poles is equal to the number of carbon brushes. Now let's discuss the second type of armature winding, which is called wave winding. And in wave winding, the total number of slots cannot be the integer multiple of the number of poles, right? So if the number of poles are equal to 4, then the total number of slots or total number of conductors cannot be 20 or 24. So they must be either 22, 18, or 26. And in that case, the pole pitch will be calculated by assuming yp equal to z plus minus 2 divided by p. So either you can add 2 and then divide it by number of poles, or you can subtract 2 from z and then divide it by the number of poles. So the pole pitch in this case can be either equal to 6 or 5. So the back pitch and front pitch in wave winding is always equal. So both these two pitches are always equal, and they must be equal to the odd number, right? So the pole pitch can be either 5 or 6, but we have to choose the odd number among these two. So odd number is equal to 5. So back pitch is equal to 5 and front pitch is also equal to 5. And in simplex wave winding, we will see that the total number of parallel paths are always equal to 2. So we will check this at the end of our wave winding, right? So let's start performing the wave winding, starting from the slot number 1, right? So this is wave winding, and in this figure you can see that our front pitch is also equal to 5 and back pitch is also equal to 5, and we have total 4 poles. This is the first north pole, and south pole, and this is the again first north pole. And now we cannot use equal conductors for each pole, right? Because total number of conductors are 22 and the number of poles are 4. So for first north pole, we will assume 5 conductors. For the south pole, we will consider 6 slots or 6 conductors. For the next north pole, we will consider 6 conductors, and for the last south pole, we will consider 5 conductors. In this way, we have used 5 conductors for this north pole and 6 conductors for this north pole. Similarly, we have considered 6 conductors for this south pole and 5 conductors for this south pole. So the total number of conductors in front of north poles are equal to 11, and total number of conductors in front of south pole are also equal to 11. So 11 plus 11 is equal to 22. So you can also consider 6 number of conductors for this first north pole and 6 number of conductors for this first south pole, and 5 for these north and south poles. So it's up to you. But the total number of conductors for the two north poles and for the two south poles must be equal. So in that way, your winding will always be correct. So let's start from the slot number 1, and back pitch is equal to 5. So 1 plus 5 is equal to 6. Now front pitch is also equal to 5. So 6 plus 5 is equal to 11. Now 11 plus 5 is equal to 16. 16 plus 5 is equal to 21. And 21 plus 5 is equal to 4. And 4 plus 5 is equal to 9. So this is our conductor number 9. So 9 plus 5 is equal to 14. And 14 plus 5 is equal to 19. 19 plus 5 is equal to 2, and 2 plus 5 is equal to 7. 7 plus 5 is equal to 12. 12 plus 5 is equal to 17. 17 plus 5 is equal to 22. 22 plus 5 is equal to 5, and 5 plus 5 is equal to 10. 10 plus 5 is equal to 15. 15 plus 5 is equal to 20. 20 plus 5 is equal to 3. 3 plus 5 is equal to 8. 8 plus 5 is equal to 13. 13 plus 5 is equal to 18. 18 plus 5 is equal to 1, right? So we started our winding from slot number 1, and we are ended up at the slot number 1. It means all winding has been completed, and we must check at the end that all the slots have been considered and no slot has been repeated. So slot number one, you can see is connected from the up top side and it is also connected from the bottom side. Similarly, slot 2 is connected at the bottom side and it is also connected at the top side. Slot number 3 is connected at the top side and it is connected at the bottom side. Slot 4 is also connected at the bottom side and it is also connected at the top side. Slot 5 is connected at the top side and it is also connected at the bottom side, and all other slots have also been connected to the other slots. So it means winding has been completed and it is correct. Now let's examine the number of parallel paths. So number of parallel paths are equal to 2 because this is our negative terminal, this is our positive terminal. All other commutator segments are the dummy segments. There is no net flow of current in this segment, in this segment, this one. Similarly, all these segments are also dummy segments, but only these are the two segments where we can see the net flow of current either into or out of the segment. So from negative to positive terminal, we can consider the number of parallel paths and we can check all the conductors and mark them over here. So starting from this path, this is the first conductor, which is the conductor number 6. Then we will move to conductor number 1. Then we will move to conductor number 18 and so on. And at the end, we will end up at the conductor number 17. And at this conductor number 17, we will have the positive terminal. So this is our positive terminal. Again, we will start from this slot number 11 and 11 is connected with 16, 16 is connected with 21. So 11, 16, 21 and so on. And at the end, we will end up at the conductor number 12. So this is our conductor number 12 and it is connected to the positive terminal. So these are the two parallel paths which are always equal to 2 in case of wave winding, right? Okay, so you can see for wave winding, A is equal to 2 always, number of parallel paths, and wave winding is suitable for low current and high voltage applications because you can see in wave winding we have only two parallel paths, so current will be small, but the number of conductors in one parallel path is very large. So we have more conductors in one parallel path. So the total voltage will be high. So for high voltage and low current applications, we will use wave winding, and the lap winding will be used for high current and low voltage applications because in lap winding we have more number of parallel paths, but the number of conductors in one parallel path are small. So voltage will be small and current will be high in case of lap winding. So that is all about our today's lecture, and I hope you have understood how the lap and wave winding at the armature of the DC generator can be done. And for watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.